Section 12, confidence intervals for means. In Section 10, we talked about confidence intervals for proportions. In Section 11, we talked about hypothesis tests for proportions. Now in Sections 12 and 13, we'll do the same exact things, but for means, for the averages of numbers in populations. So here goes. The logic of a confidence interval, as we saw in Section 10, the logic of any confidence interval is that it's statistic plus or minus margin of error. Now the statistic, as we saw in Sections 8 and 9, is typically normally distributed, although later on in the course that may get a little bit complicated. It's certainly true for the moment. And if something is normally distributed, then we're talking about a number of z's, which is the number of standard deviations. What's standard deviation? The standard deviation of the thing in question, the statistics standard deviation. Hence the logic of how our confidence interval formula worked. It was statistic, p hat, plus or minus z, times standard deviation of statistic. Well, from Section 8, we know it was supposed to be the square root of p times 1 minus p over n. But of course, if you knew p, you wouldn't have to estimate p, so we had that fudge factor of the hat in the formula. So it's the closest thing we have to statistic plus or minus z times standard deviation of statistic. The logic for means will be exactly the same. What we have is x bar, the average of the numbers in the sample, estimating mu, the average of the numbers in the population. So a confidence interval for the population average, the average of all the numbers out there, is estimated by the average of the numbers you actually pick. We know from Section 9 that x bar is approximately normal for various reasons, either because what you're picking from is normal or because the sample is large. But for confidence intervals, we want large samples anyway, for reasons that we've begun to see. So x bar is normally distributed with mean mu, centered at mu, with standard deviation, the standard deviation of the population divided by the square root of the sample size. There you go. So statistic plus or minus margin of error. There's the margin of error. Statistic plus or minus z times standard deviation of statistic. So there's the standard deviation of x bar. So if you know the average of the numbers that you picked, which of course you do, it's your estimate, and if you know the confidence interval you're looking for, and if you know these guys, then you're good to go. Do you know the sample size? Of course you do. The z comes from the same row it always came from, just like in Section 10. If you want 95 in the middle, then you want 1.960 to either side. We'll cut it off. So the exact same row on the normal chart that we had before, the row in some of these sections. So we know this, we know this, we know this. Really, it comes down to whether you know sigma or not. And this is where it gets a little bit complicated. The easiest way to do this is to assume that you know how the population varies. To assume that sigma is known. Yes, it's a little bit artificial. You don't generally know anything about populations. But remember, it's mu that we're trying to estimate. That's the unknown. If we assume that we know sigma while we're looking for it, then it makes this that much easier. The less you're sure of, the more estimating, the more randomness enters into it. We'll talk about that in Section 18. For the moment, we'll assume that you know the standard deviation of the population while you're looking for the mean. You don't know where the population centers, but you do know how it's spread out. That is not as contrived as you might expect. Take our assembly line examples, where the nozzle doesn't always squirt out the same amount, but how much it squirts out on average is our unknown. That is got to do with how the machine is calibrated. On the other hand, how it varies from squirt to squirt has got to do with how the machinery is constructed. So it's entirely possible that you could know how it varies from squirt to squirt without knowing what it's calibrated to chuck out on average. In any case, it'll be a lot easier if we know sigma, and if we don't, we'll talk about how to modify these procedures in Section 18. It gets a little complicated. Example 1. A forest has mean tree height we don't know, all the trees, millions of trees, population, and standard deviation 5 feet. For some reason we do know how trees in this forest vary in height. We wish to approximate the average tree height of the forest, mu. We take a simple random sample of 100 trees, that's our n, and the average of those 100 numbers, data, x bar, statistic, is 15. So that's my x bar. Notice, by the way, that from the same information we can either find a confidence interval or we can test a theory, just as we did in Section 10 and 11. In this section, we'll talk about confidence intervals. 95% confidence interval for the average tree height of all the trees in the forest is x bar, 15, plus or minus the z. The 95% from our little row there gives us the 1.960, exactly as it did in Section 10 for proportions. Sigma is 5, known, easy enough, put it there. Sample size, square root of 100, figure it out, 15 plus or minus 0.98. 0.98, 15 feet. 15 feet plus or minus 0.98 of a foot. Same units you started with. The meaning of it is exactly as it was in Section 10. A 95% confidence interval for the average height of all the trees in the forest is 15 minus that to 15 plus that. 1402 to 1598. We are 95% confident that the average height of all the trees in the forest is between those numbers. We're 95% confident that the average height of all the trees in the forest is 15, with a margin of error of 0.98. Different ways of saying the same thing. Low end, high end, center, radius. Assuming our sample is among the 95% most typical samples we could have gotten, the average height of all the trees in the forest is between 1402 feet and 1598 feet. The 95% confidence interval says that the truth will be between the walls if you happen to pick one of the 95% most typical samples you could have picked. Of course, you've got no way of knowing that. Without knowing what things are centered at, they're centered at mu. But if you don't know mu, that's not a big help. So we have no way of knowing if the sample we just got was a typical one or a very unusual one. But assuming it was among the 95% in the middle, the truth must be between the walls. Another way you could say that, 95% of statistics you could get, 95% of samples you could do, will generate walls that do contain the truth. That's what it means to be 95% confident that it's between the walls. Remember, mu is what it is. It can't be other than it is. There's nothing random about it, only unknown. What was random is what we're working with. But assuming the sample was among the 95% most typical we could have gotten, the walls that sample generates will contain the truth. The flip side of that is, unless our sample happens to be among the 5% most unusual, the 5% in the tails, 2.5 either way. Unless that's the case, then the truth is between the walls. Notice the confidence intervals use exactly the same chart as before. It's on the normal chart. It's at the top of Section 10. It's at the top of Section 12. Anywhere you're going to need it. 1.960 for 95% confidence. On the other hand, if you want 99% confidence, then we'll use the 2.576. Notice, by the way, that if you want more area in the middle, you're going to have a bigger z to either side. And since you're multiplying by it exactly as with proportions in Section 10, it'll give you a wider margin of error. That's actually 0.2 down here. If you want a higher confidence level, then it'll give you a wider margin of error, because if we multiply by 2.576 instead of 1960, it'll give us a bigger margin of error, 0.138 instead of 0.98, I believe it was. A 99% confidence interval for the average height of all the trees in the forest is low end lower, high end higher, 1362 to 1638, wider. Bigger radius, further in either direction from 15. We're 99% confident that the average height of all the trees in the forest is between the walls. We're 99% confident the average height of all the trees is 15 with a margin of error of 1.38, the way a journalist would say it. Assuming our sample is among the 99% most typical samples we could have gotten, the truth is between the walls. If it's among the 1% outlying, the truth is not between the walls. Unless our sample happens to be among the 1% most unusual samples we could have gotten, the average height of all the trees in the forest is between 1362 and 1638. The other point from Section 10 also remains that a larger sample size will give you a smaller margin of error. Note the formula. We have an n on the bottom, so if you have a bigger sample size, then all other things being equal, you'll get a smaller margin of error. The difference is, here, unlike in Section 10, all other things really are equal. If you pick a bigger n, you're probably going to be using a different b hat. So that's a bit hit and miss. But here, sigma is what it is, z is what it is. If you pick a bigger sample, you're going to get a smaller margin of error. And by the way, notice that nothing here depends on what the sample happens to be, unlike in Section 10. There you go. So, back to our point, a larger sample size will produce a smaller margin of error. For the sake of argument, we'll do a sample of size 1,000 and get an average tree height of 15 feet. Now, bear in mind, if we pick 900 more trees, we're not going to get the same average from the sample, but for the purposes of comparison. Well, bottom line, we have 1,000 on the bottom line instead of 100, and that makes it all the much smaller. Instead of 0.98, it's now 0.31. You don't go so far to the low end bigger. You don't go so far to the high end smaller. A tighter margin of error, smaller. A 95% confidence interval for the average height of all the trees in the forest is here. We're 95% confident that the average height of all the trees in the forest is between the numbers. We're 95% confident that the average height of all the trees in the forest is 15 with a margin of error of 0.31. Assuming our sample is among the 95 most typical samples we could have gotten, the truth is between the walls. Unless our sample happens to be among the 5% most unusual samples we could have gotten, the truth is between the walls. A larger sample will give you tighter results in every sense, and that's also common sense. On the other hand, I think it's also common sense that the more confident you want to be about where it is, the bigger space you've got to give it to live in. All points that we made in Section 10, all still true for all the same reasons. As before, we can figure out the minimum sample size required. But if we know sigma, then we don't have any hit and miss, worst case scenario, wild guess stuff going on. It's just a matter of algebra. It's just a matter of if m has got to be this, then solve for n. And it just ends up being this. So if m represents the margin of error in whatever units you've got, feet, confidence level gives you the z, sigma is given at the start of the problem, and of course you've got to round up to the next whole number. If it's between 63 and 64, then 63 is not enough, 64 is. It's not about the rounding exactly. You've got to bump it up to the next whole number. What sample size is required to be 95% confident that our sample mean will be within 0.1 foot of the truth? Well, for a sample of size 100, it was 0.98. For a sample of size 1,000, still 95 confidence, it was 0.31, so more than 1,000. Bigger sample to make a smaller margin of error. So considerably more than 1,000, but how big? Well, fill everybody in. 95% confidence gives us the 1.960. Standard deviation 5 given, 0.1 of a foot, margin of error, multiply, divide, square. In this case, it is a whole number, if I recall, but go up to the next whole number in any case. How badly do you want to know? If you want to be 95% confident that you have the truth to within 1/10 of a foot, then you've got to look at almost 10,000 trees. So, good to know before we start measuring trees. What if the standard deviation of the population is not known? Well, short answer, we'll talk about this in Section 18. But if the sample is size 1,000 or more, really big, then it doesn't really matter. You see, the idea is that if we don't know sigma, then we're going to have to estimate it with the thing that estimates sigma. The standard deviation of the sample, S, section 2, those 100 or however many numbers, estimates sigma. Now this gets a little bit complicated because additional randomness will make the thing more random. So we'll talk about that a bit later. But if the sample size is very large, say over 1,000, then it's not going to make too much of a difference. You don't really have to know this. It'll be very obvious when we talk about it in section 18 just by looking at the numbers. So for the time being, we'll assume that we know the standard deviation of the population while we're looking for the standard deviation of the sample. That's section 18. Take a look at the problems for section 18, and when you're ready, try the quiz. Questions, as usual, will go to the discussion area so that everybody can benefit.